getting it. Yeah, I love it. So today we're going to be talking about Nikola Tesla, the Tesla coil, and the science of electricity. So who here likes to watch television or play video games or maybe mess around on your cell phone? Yeah, I see a couple of you who like to do that last one.
Right.
Alright, so did you know that those things are only made possible thanks to Nikola Tesla's inventions? Like he created the alternating current system that we use in our homes in our wall outlets. So anytime you plug something into your wall, you need to be thanking Mr. Nikola Tesla because he's the one that made that possible. And on a larger scale, we can use places like Niagara Falls to generate electricity, and then using that same alternating current system, transmit it to anywhere we need it in the United States.
What about a generator?
So, what about the radio? Do you folks like listening to the radio?
Yeah.
I know I do. But did you know the radio itself was only made possible thanks to Nikola Tesla's patents? And in fact, by the time he died in 1943, Nikola Tesla had over 250 patents to his name. That's over 250 inventions. So it's no wonder that Albert Einstein himself called Nikola Tesla the world's smartest man. So let's move on to Mr. Nikola Tesla's most famous invention, in my mind anyway. It's the Tesla coil. So we saw the Tesla coil produce a whole bunch of lights and a lot of electricity, but what was it actually designed to do? Nikola Tesla had a dream, and that dream was to power people's homes wirelessly. And he wanted to do it for free as well, which I would have really appreciated. What about you adults?
Oh, yeah.
Yeah, I know. But while the free thing didn't happen, he was indeed able to transmit power wirelessly. And our Tesla coil is a good example of this. Did anyone happen to notice the neon Tesla coil sign inside the cage here? Alright, so did anyone happen to notice what it was doing while I had the Tesla coil turned on? Glowing. It was glowing. Absolutely. But you see, the special thing about this neon sign is that it's not plugged in. And in fact, it can't be plugged in because the plug fell off a couple days ago. So it's just sitting there on its wooden stand, and it's being powered wirelessly. So this shows that Nikola Tesla was absolutely able to do what he wanted. So how does it work? Well, our Tesla coil actually has two coils. It has a primary coil, which is the big copper one on the wooden stand there. Let me turn the light on so you can get a better view. The one that's just kind of short, it's about that tall, and it's kind of loosely wound around the rest of the coil. That is the primary coil. When I turn this key, we're pumping electricity into that primary coil. And when I press the button to activate the Tesla coil, it sends that electricity into the secondary coil, which is the big red cone that you see there. Or orange if you're kind of colorblind. So when it hits that secondary coil, it gets upped in voltage and it gets transformed. And then after that happens, it gets sent into the discharge sphere, which is where the electricity arcs off from onto the cage. So we're producing arcs of about 1.5 million volts.
Wow.
So that's pretty dangerous, right folks?
Yes.
Absolutely. So what's protecting us from all that electricity? I hear someone say the cage, and I heard it from over in this direction. And you're absolutely right, it is the cage. So our cage is special. It has a name. It's called a Faraday cage. And it was invented by a British scientist named Michael Faraday, who discovered that if you place grounded metal in between yourself and an electric discharge like our Tesla coil produces, then the electricity will strike that grounded metal each and every time. Wouldn't exactly recommend trying to discover something like he did though, because he used himself as a guinea pig, and that's not exactly the safest thing. But because of him, we created our own Faraday cage that's made of 2.5 tons of grounded steel, just to keep us safe. But we can all clearly see that there's bunches of gaps in this cage, right? You can see I'm sticking my hand through it, right? So is there any electricity getting through those gaps? Raise your hand if you think, yeah, there's got to be at least a little bit of electricity getting through. All right, raise your hand if you think, no, there's no way there's any electricity getting out of that Faraday cage.
Raise your hand, Papa.
All right, so we're in a science museum, and we have to experiment and test our theories. So here I hold a neon tube light. It's exactly like the ones making up the neon Tesla coil sign inside the Faraday cage. I'm going to set it on this stool here, just outside of our Faraday cage. And I'm going to turn on the Tesla coil again. Can you folks see it? Alright. So, I'm going to turn on our Tesla coil again. And we're going to see what happens to that neon tube light. If there's electricity escaping, it should light up, right?
Yes.
Right. So, are you folks ready for me to turn on the Tesla coil again?
Yeah.
Alright. So let's get this thing fired up. And 5, 4, 3, 2, 1. All right. So what was happening with the neon tube light?
Nothing.
Nothing. Absolutely. So this shows that our Faraday cage is doing exactly what it was designed to do, and it's keeping us safe from all that electricity.
And sharks.
So back to Mr. Nikola Tesla for a moment, because he was a very busy individual during the late 1800s when he designed and created these neon tube lights. And he demonstrated them at the 1893 Chicago World's Fair, where he lit up the entire fair with them. And he did it wirelessly. And this astounded a lot of people. I mean, wireless lights are even pretty cool to this day. But one thing that Mr. Nikola Tesla did not do was he did not patent these. So anyone could take them, copy them, and sell them as their own. So another thing that Mr. Nikola Tesla did was he did a lot of early work on fluorescent lighting, much like our modern bulb here. And we see these all over the place nowadays, right? You know, see them everywhere.
Yep.
One of the reasons probably why we see them everywhere is because just like his neon tube light, Mr. Nikola Tesla did not patent his work on fluorescent lighting either.
And he's way ahead of his time.
So has any of you folks ever had an X-ray, or do you know someone who's ever had an X-ray? All right, so pretty much everyone has or does. So X-rays are no big deal nowadays. They're pretty common. But back in Nikola Tesla's time, that was not the case at all. They were cutting-edge technology. They were brand new. And in fact, Nikola Tesla was one of the first scientists to ever take a full-body X-ray of himself and then live afterwards. You know? Which is kind of the important part, right? But just like with his work on fluorescent lighting and his neon tube lights, he didn't patent his work on X-ray technology either. But one thing that he did patent was called an inert gas discharge tube. And he created it to be a direct competitor with Thomas Edison's incandescent light bulb. So, obviously the light bulb won that competition because when I say light bulb, you all know exactly what I'm talking about. But when I say inert gas discharge tube in a crowded room, well, I get a lot of looks like a giant nerd, right? You know, like you guys are kind of looking at me right now. But nearly a century after Mr. Nikola Tesla, an American artist named William Parker
I'm
made
smaller
that
than
inert
you.
gas discharge tube, and he thought, you know, I can do something neat with this. And so he surrounded it in a glass dome, and he filled that dome with different gases, and he gave us the plasma globe. Alright, so our plasma globe is filled with a variety of different gases, mostly nitrogen, neon, xenon, and krypton. And those are what give you the different colors. And the pink globe in the center is very highly charged with electricity. So when I ground it out by touching my hand to the outside, an arc of plasma jumps to my hand. So what exactly is plasma? I've been saying it a lot. Well, plasma is the fourth state of matter, kind of like a solid or liquid and a gas, right? Except it's what happens when you pump a lot of energy into a gas. And some common things that are made of plasma are things like lightning bolts and the surface of the sun, so you know nothing big. But now that you know that there's a lot of energy in that plasma, what's keeping my hand safe from the heat and the electricity? The glass, absolutely. After all, glass is an insulator. It doesn't let electricity travel through it easily? But is it keeping all of the electricity inside, like our Faraday cage does? Raise your hand if you think yes, it is keeping it all inside. Raise your hand if you think no, there's no way that glass is keeping it all in. All right. So again, we have to experiment and test our theories. And remember, our friend the neon tube light here lights up in the presence of electricity.
Because if you touch it, it makes your hair
So, now that we know there is indeed electricity coming off this plasma globe and that it will light up a neon tube light,
That's cool.
what about other types of lights? So, here in my right hand, I hold a incandescent light bulb made famous by Mr. Thomas Edison. And here in my left hand, I hold a fluorescent light bulb whom Nikola Tesla did a lot of early work on. So, who thinks that the fluorescent will light up when I touch the plasma globe? Who thinks that the incandescent will? Remember, this isn't like election time. You can vote more than once.
I vote both.
Alright, so, let's find out. In 3, 2, 1.
Oh, it is. Cool.
So it has to be the one that's filled with gases.
Alright, so it looks
Yeah.
like the
Other one.
fluorescent
Yeah.
is working, but the
So you
incandescent
should have picked yourself.
does not. So that means, sorry, Mr. Edison, but you're kind of boring. So now that we know it'll light up one fluorescent, what about two?
Yeah.
Well, let's test it out.
Cool.
Turn down the lights.
Cool.
All right, testing two fluorescents in 3, 2, 1.
Oh, cool. Yeah.
All right.
Okay.
So there is enough electricity in the plasma globe to light up two fluorescent lights. And now the most important question I'm going to ask you today is, don't you think they look like eyes?
Yeah. Cool.
All right. So now that we're done being silly, we can move on to the next part of our show. And it's the most difficult part for me because now I have to find the light switch in the dark. All right, there we go. So we know that people conduct electricity, right?
Right.
That's why we don't stick our fingers in the light sockets and why we don't stick forks in the wall outlets, right?
Right.
Right? All right. I don't want to hear about any of you folks going home and doing either of those things, okay?
Yes, sir.
Okay. And if you do it, you didn't hear about it from me. So, who thinks that I can place my hand on the plasma globe, conduct the electricity through my body, and then light up the fluorescent light in my other hand? Who thinks I can do it? Who has no faith in me whatsoever? All right.
You can do it.
So, one person who has no faith. All right. So, let's try this out in 3, 2, 1.
Oh, no. She had faith in him.
It looks like I'm just not electrifying enough to do it on my own. But you know, if I had a volunteer up here to help me out, I saw her hand come up first.
Oh. All right.
All right, honey, what's your name? Shelby? All right, so what I want you to do is stand right about here. That way everyone can see you. Face the audience. And then,
I wonder if her
all
hair
right,
will
so I'm going
start
to hold
standing
out the fluorescent light like this. You're going to place your hand flat out above it. Flat, fingers together. And then you're gently going to lower your hand until it's on the glass, okay? All right, try it out. Just like that. Lift. All right. Testing. Now.
Cool.
All right. So why is it working now?
Oh, why?
We're creating what's called a closed electric circuit.
Oh, cool.
A couple things you got to remember about electricity. Electricity likes to take the path of least resistance to the ground, right? So right now, that path is through me, through the fluorescent light, through Shelby, and then into the ground.
Why was it resisting the other way?
Why was it not going through the other way?
Well, with just you holding it.
Well, if Shelby will move her hand up a little bit, is the light in any way in between myself and in the ground?
Oh, okay.
All right. That is the reason why. Why would it go to the light when the light's not connected to the ground?
Gotcha.
So go ahead and put your hand on there.
Cool.
All right. So why doesn't it just go through me and into the ground? Well, electricity, it won't take the